Hello and welcome students, welcome to my channel. In this video, we will be discussing questions based on thermodynamics which were asked on 27th of January 2024. Now this video is in continuation with the other videos students. Kindly you are requested to go through the other videos as well. Okay, so all the videos have been subdivided topic wise or chapter wise as per convenience, and I have also showed the technique of calculating. Okay, in certain cases you are not supposed to fully calculate the answer because unnecessarily you will be losing time. So because time, as I said, is the most important resource in the exam hall other than knowledge. So in spite of having full knowledge, if you are not able to save time, if you are lavishly spending time like anything, you might end up in a troubled manner. I mean, you might be missing certain questions because of lack of time. So in order to avoid all such situations, you have to very wisely spend the time. So one of the art in spending time usefully is you are supposed to reach the answer as close as possible without actual calculating. So I have been showing this technique in all the video students, and you are requested to become habitual to this kind of a way of solving. This is how the toppers solve. They don't fully calculate it. They just try to come as close as possible to the actual answer. Okay, right. So without wasting time, let us start this in continuation with the other questions. Here comes question 23. A mass of 0.08 gram kg air is heated at constant volume to 5 degrees Celsius. The specific heat of air at constant volume is given and change in its internal energy. Now students, you have to apply the first law of thermodynamics. So first law of thermodynamics says that in a constant volume, in a process in which volume is constant, work done is zero. So the heat supplied is basically the change in internal energy. So even though we are being asked to calculate the change in internal energy, we will be using heat supplied. And heat supplied, since they have given mass and specific heat capacity in terms of mass, so we will be using ms delta theta or delta T formula. Okay, even though usually we use number of moles and molar heat capacity for gases, but they have furnished the details in terms of mass and specific heat. So naturally we will be using ms delta theta. So mass of the air is 8 by 100. See student, I have not written this as 0.08. I have written it as 8 by 100. These small techniques will help you save a lot of time. Then specific heat capacity is 0.17 kilo. Kilo I will merge it here. So kilo is 1000, so it becomes basically 170 calorie. Calorie to be immediately converted into joule by multiplying by 4.18 joule per kg degree Celsius. So all are in SI unit, so not a problem students. I am not writing as unit to avoid unnecessary confusion. I am proceeding exclusively in SI unit. Then coming to change in temperature, change in temperature is 5 degrees Celsius. So this should give you the answer. Now how to actually calculate it? See students, you have to be very careful, okay, very careful, and you have to reach as close as possible to the actual answer. So here you see, you have 5 2s are 10, 2 4s are. So you have 17 into 4 4s are 16, and slightly more than this, you can approximately take it as 17. So what is the square root of 17? 289. So you can seek an answer closest to 289, which is clearly equal to 284. Of course, here you have one more option quite close to this, but anyway we are on the higher side, so the actual answer we will be looking for will be less than 289, because instead of 16 point something we have made it as 17. You can see students, okay. So that's how you are supposed to solve it. Moving on to the next question, question number 24. The average kinetic energy of monoatomic molecule is this at temperature. As you know, the average kinetic energy of any particle is given by 3 by 2 times Boltzmann constant into T. Okay student, 3 by 2 kb into T. So this is 3 by 2 into Boltzmann constant is clearly given as 1.38 into 10 to the power minus 23 joule per mole Kelvin. Average kinetic energy we have to convert it into joule, of course. So this will be 0.414 into 1.6 into 10 power minus 19. So from here you can find the temperature. Okay, now here a little bit of smartness is required, students. You can see that this will be numerically equal to 414. This 4.14. So 0.414 multiplied by 10 times will give you, okay, right. So we have this 1.6 into 2 into, here you have 10 power minus 22, which goes that side becomes 10 power plus 22. 22 minus 19 is 3. So this is 3.2 into 1000. So this is 3200 Kelvin. This is how you are supposed to calculate. Moving on to the next question, students. During an adiabatic process, the pressure of a gas is found to be proportional to the cube of its absolute temperature. We have to find gamma. Cp by Cv we have to find gamma. So here they have given pressure is directly proportional to cube of temperature. As we all know, Pv power gamma is constant, isn't it? Now for a fixed mass of a gas, we can replace P by Pv by Nr. Bringing this P to this side, we can have P square V cube is a constant. Remember, power of P should be 1, so we have to extract square root. So when we extract square root, we get a new constant. So you can see gamma is 3 by 2. You can compare this with this, right? Then moving on to the next question. The total kinetic energy of 1 mole of oxygen at 27 degrees Celsius is this. Now as you know, the total kinetic energy of any gas, okay, per degree of freedom per mole is this. You have to remember this. If n is the number of moles and if f is the degrees of freedom, you have to multiply this. Okay. So R is 8.31 joule per mole Kelvin. Temperature we have to convert this into Kelvin, which will be 300 Kelvin by 2 into number of moles is 1. So N is 1, and for a oxygen is a diatomic gas, you can take 5 as the degrees of freedom. You can see temperature is not very large, so you don't have to consider the degrees of freedom corresponding to vibrational motion. Okay, because those modes get activated only at sufficiently high temperatures of the order of beyond 1000 Kelvin. So that is not required here. Right, students? Alright. So how to calculate this? Again, you can see how we are about to calculate. I will multiply this by 2 and divide this by 2. So that is becomes 10. This is 4. So 8.31 will be 4. Slightly something, maybe 4 point something, because 31 divided by 4 is how much? 0, not even 1, less than 1. Okay, students? Into 3000. Sorry. Let us see this. What I am doing. 8.31 and this is 2 by 2 is 4 into 3000 because this is 10. So this will be 2 point slightly something, not even 1, less than 1. So I take it as 1. Okay, students? So this will be 2, 3 is 6, slightly more than 6. So this is the answer. This is how you are supposed to calculate. Okay, students, so that's all in this video tonight. Thank you so much for watching my channel.